Good day to you all. Thanks for joining this video. Today we're going to talk about solar pumping. My name is Peter Albeda. I'm a solar energy expert and I'm working for PUM. What will be discussing today? I'll give you a brief introduction in solar pumping. We'll look a bit more into irrigation. We will try to find out how to size the capacity, and we'll look in cost and benefits of solar water pumping, and we will look into some of the practical solutions and components that can be used, and we will do a case example, and we have some exercises. Well, as I said, many application possibilities for solar pumping, irrigation, drinking water for cattle, and last but certainly not least, drinking water for people. So let's look very schematically how solar pumping works. First, we have a solar resource, which is the sun, of course. And then, secondly, we have a solar array, a PV module, where the sun is captured, put into electricity. Then third, we have a pump controller, which transforms the energy from the panels to the energy of the pump. In general, we would like to use a DC pump. If we want to have a AC pump, then we in general also need a DC to AC converter. Well, then fourthly, we have a water source, which in general will be a well, but of course this could also be, for instance, a river or something like that. Then 5, we have a submersible pump, which can be used to pump up the water. Then 6, we will in generally have a water storage facility in for instance, a tower. This is very important because the sun is not always there. So if there's no sun, you still want that there is a flow of water. So then you pump when there's sun, and you use the buffer when there's no sun. Then you have a distribution network for the pumped water, and you'll have a water demand. This is how it generally works.
Millions of people around the world live in rural villages with limited access to water. In many communities, the deep groundwater is extracted via electric water pumps. But electricity is often not available, so the electric pumps have traditionally been powered by diesel generators. These generators bring a range of challenges to the rural communities. There are lots of moving parts, which means every month they need a service, and twice a year a major service is required. Costly, cumbersome, but critical to avoid breakdowns. And of course, a generator runs on fuel, which is both expensive and emits carbon dioxide. So for the life of the generator, the community is continuously paying for diesel, maintenance and replacement of parts. So what are the alternative sources of power for our pumps? What about solar? People often say solar panels are expensive, and they once were, but prices have been tumbling, and in the last 7 years, the price has dropped by 80%. And now these panels last for more than 25 years. Let's compare the cost of a diesel versus solar power solution for pumping water. Well, the initial cost of solar is higher. But over the lifetime of the pumping system, replacement parts and maintenance costs are far lower. And then what about fuel? The generator keeps consuming diesel, and the solar, well, sunlight is free. So, by choosing solar, you've helped to reduce the cost of accessing water by using clean energy in your community for the next 25 years. It's becoming increasingly evident that solar is simply better. To learn more, go to www.worldbank.org/solarpumping.
So the conclusions in these videos are quite clear. They said, and it's true, that the initial investments for solar is higher than diesel generators, but solar has great advantages. It's clearly more reliable than diesel engines, less maintenance. Solar panel currently last 20 years or even 25 years. No more investment in fuel after the initial investment in solar. And of course, last but not least, we have sustainable energy. So since the cost of solar have decreased largely in the last years, this has shortened the payback time considerably. Now let's talk about irrigation. In general, there are two forms of irrigation, with and without storage. When we start a SVP project, first we got to do is determine what the water consumption is. In this sheet you see some examples of the liters per day. For each situation you have to calculate what's the actual water consumption that we need. We also have to consider the availability and season dependability of the water demand. And last but certainly not least, we have to consider the water quality, if that's good enough. And when we do irrigation, we also have to ensure the sustainability. And one of the ways we can improve irrigation is to have efficient water use by drip distribution. When we are deciding on solar powered irrigation systems, we first have to investigate the local conditions. What's the slope that we have there? What's the soil type? What's the effective rainfall? These are local conditions that are very much specific for that location, of course. Then we have to look at the sort of irrigation that we want to do. For instance, what's the groundwater level, and what water source do we have, and we have to look into legal things like what right do we have to use it. Then there are different water resources and which can we use. Then if we know how the local conditions are, we know our demand, we know what kind of irrigation we need, and what water resources we have, we have to look into the economics and the viability to use solar pumping. But in general, as explained earlier, the business case is quite good for solar pumping. We will present here a tool example. This is a toolbox solar-powered irrigation systems. It can be found on the internet. The tools that are included is the pumping sizing tool, helping you to find out how big your pump should be. There's a payback tool which can help you in the business case for solar water pumping. Market assessment tool, water requirement tool, and farm analysis tools. When you set up irrigations, the steps are you look at the preconditions, you do the planning, you look at the economics, then you select the components, and then you look at how will we manage this system when it's installed. And the toolbox example supports all these steps. This is a slide which I won't get into, but this explains all the steps I just described and how the tool supports them. To explain this in detail is beyond the scope of this course. Then we look at a very important part for solar water pumping, and that's capacity sizing. What we have to do is first look at the hydraulic energy, so the demand of energy that we need to allow solar pumping. First, we have to define the water volume and the needed flow rates. We have to make a layout of and sketch and the distances, because as explained, the distances and for instance the slope which needs to be bridged, the height that has to be pumped from where the water is to where the storage is of the water, and then from the hydraulic energy we calculated, we look at the electrical energy needed. And when we do that, it's very important that we compensate for motor pump losses. Then, if we know how much electrical energy is needed, we define the solar capacity that we do that, and we have to look into what local solar resource there is. There's an online internet tool, and we discussed that later, that helps you to estimate what you can expect will be the available power of solar energy based on the solar panels you have, the way you've set up the solar panels, and your geographic location. There are two things that are important. We need to establish the flow that is needed, and the flow that's designed as a Q. How much water is required per time frame, and the flow is also addressed as the yield. And the greater the discharge flow rate, the greater the pipe diameter that is required. And one of the other terms that we see in solar water pumping is the head, and the head is defined as how high must the pump pump the water. So in fact, what's the pressure that we need to get the water on the right level. And then we have the TDEH, and that's the pump head plus friction head and the drawdown. These are all terms that we have to consider when we're doing our solar water pumping calculations. There are two terms I'd like to introduce here. The head and the drawdown, the friction head and the drawdown. The friction head should be seen as the extra head, extra power needed to compensate for pressure losses in the pipework. As a rule of thumb, in general we need about 10% extra head of all horizontal pipe lengths to account for the friction head. Then we have the dynamic drawdown, and as a rule of thumb, suppose we have a discharge flow rate, AQ, of 1 cubical meter per hour. That will cause a dynamical drawdown of 1 meter. And for example, if we have 8.5 cubical meter per hour, then we will have an 8.5 meter drawdown. So here we put out the different parameters that we need when we calculate the hydraulic energy. So let's do a TDEH example. Suppose we have a demand of 60,000 liters or 60 cubical meters per day, and say that we are able to pump during 7 hours per day. So the flow rate is 60 divided by 5 is 8.5 cubical meters per hour. Say the total dynamic head, say the water depth is 100 meters, say the storage height is 10 meters, the dynamic drawdown is 8.5 meters, and that's subtotal 118.5. Say we have a 10% friction head, then we need 12 meters extra, so the total dynamic head will become 140 meters. Remember that we said in the last sheet that we need 10% extra. And also we have to consider that when we do irrigation, also the irrigation system itself will need some additional pressure. So we have to add that as well. So we'll put this in the formula that we presented earlier, and then our calculations show that we have our demand is 21.2 kilowatt hour per day. And then if we look at the electrical energy that we required to then we also have to add to this the losses that we have. We have a motor pump efficiency, and typically that's quite low, so that's 30 to 60%. Now, for this example, we assume that the efficiency is 50%. So instead of the 21.2 kilowatt hour per day, we need 42.7 kilowatt hours. So what does this mean for the solar area required? In this example has been made for Paracau Benin, and the minimum peak sun hours designated with the PSH is 4.3 hours per day in August. So to get 42.4 kilowatt hours per day, we anticipate there's a 70% efficiency of the solar powers. So we need a PV array size of 14 kVp. So for instance, if we if we see how we can put that together, then we come to an array of 48 PV modules of 300 watt each. Okay, we'll now look into estimating the solar power on a certain location. There are some factors that determine the available solar power. First, we have to know where is the location. We have to look at the inclination, which is the tilt of the solar panel, and we have to look at the orientation of the solar panel. That can also be different, and remember that the orientation is never 100% efficient, because you are always, well, the sun is also traveling in the air, of course, but we have to, and you cannot always point the solar panels in the most favorite location, unless you would use a solar tracker, which we usually don't use. And then the solar power is also dependent on the season of the year. So there are two ways of determining the solar power that we can expect. We can look at the peak sun hours, which we can get from tables, but there's also a online tool called PVGIS, and there we can type in all these different things that we just look into, and then it will calculate what is the expected solar power at that location with that inclination, that orientation in this season. Then I would definitely like to advise you to look at the free tools that are available online. Follow this link, and there's a great toolbox that you can check out. There is also a design pump sizing tool. You can look at the water requirements for crops and livestock, rainfall season, soil and irrigation, farm profitability checklist. These tools are available in English, French, Spanish and Arab. So I would suggest to look into that. Then very important part of this presentation is about cost and benefits. We're going to look into an example from a practical case where we looked into the solar versus the diesel pump. We looked into the capex, what the initial investment was for a diesel pump, what the initial investments are for a solar pump. And then when we look into that, and we looked here for a period of 20 years, and you see that the investments on fuel during that 20 years are very high. And of course, once you have the solar, you won't no longer have to invest in pumping. And then we also have to consider the replacement costs. And if we look for a diesel pump, we will have quite some investment for the diesel pump, because the diesel pump will definitely not last for 20 years. Probably something like 7 or 8 years or something. So we have to replace the solar pump, the diesel pump, and also the pump, the solar pump itself will also need some investment. And then when you look at the total investment, then you see the life cycle costs are lower because you don't have fuel cost, and overall the business case for solar pumping is very good. Then we're going to look at some technical solutions in practice. Let's now look at two different pump types. We look into this slide in two different pumps. One is the positive displacement pump, and the other one that we compare is the centrifugal pumps. If we look at the positive displacement pump, it's good at low speed and variable solar. It's suitable for high pressure and high efficiency, and it can handle high viscous liquids. And as an example, you see a picture here of a helical screw pump. Then the centrifugal pumps are simple, and they are low cost, and they are ideal for high flow rates. They can handle emulsions with solid particles. In comparison to the other pump, it has a low efficiency, and it must be primed. And of course, you should also always, when you are preparing a solar water pumping project, you check the data sheet for the pump for the performance curve. That's important also to check what are the conditions where you use it, which is the flow, and what's the input pump power. Then we're going to look at the submersible versus the surface pump. The submersible borehole pump is the one that we saw in the example earlier. There the pump is submerged in the borehole and to pump it up from there. And then we also can have a portable surface pump, which is portable. You can easily put it somewhere else. You would use it when you have a large basin of water where you can use it on. but we have to consider that there is usually a maximum of 7 meters suction height. Then we look into some motors and control systems. As I said earlier, the brushless DC motors are very interesting because the PV system is a DC system, and then you don't need the DC AC conversion. But you can also have a 3-phase induction AC motor with variable speed inverter. So in the last example, you will need a more complex inverter to make that possible. Then, if we look at control systems, we prefer an MPPT control system which has a better output, and we want variable speed operation because you want to optimize the flow for the purpose that we have. And you would need a high-level tank sensor, for instance, to stop the pumping when the high-level tank has well, the high-level tank is full. Also, you want water flow detection for a dry run protection. The engine could get too warm and it could be damaged. Also, we need protection against low pump speed. With a low pump speed in general, the current to the pump will be higher at lower speeds, and that can also damage the pump. And we need protection against overload or high temperature. And we could have in the control system optional Bluetooth or Wi-Fi communication, remote control for data logging and monitoring. And very important in the control system that we have to ensure PV open circuit voltage is within the pump specification, that if we have a very good day with lots of sun, that the pump stays within specification. In this sheet you see some examples of solar pump suppliers, which I will not go into more detail at the moment. And then there is an interesting video that you can look at yourself if you want to know more about a practical borehole drilling with all the parts you need for it. This video is not part of the presentation, but if you are interested, you can easily find this video on the internet and watch it. It's quite a long video actually, but interesting if this is important to you. And now I'd like to present an example of a solution that we in PUM did for Benin. We talk about a power solar pump, PowerMare solar pump that we used for there. It's a DC brushless motor with a power of 500 watts, voltage 48 volts, and pump efficiency is 35%, so that's pretty good. As you may remember that we said the efficiency is between 30 and 60%, and this is an efficient one. With the pump from the factory comes a table that demonstrates if you use the pump with a certain head, what the flow in liters per minute can be and what the flow can be in cubical meters per hour. So we have to consider the head of our application, and then we can see in this table what the expected flow will be. Now, the total dynamic head, the water depth was 10 meters. Storage height is 2 meters up, and the drawdown was 1 meter. As we discussed earlier, there's a 10% friction head we need to consider. So the total dynamic head that we have to anticipate is 15 meters. And in the table, you can see that we more or less have to look at the flow of about 1.5 cubical meter per hour. And it will be a little bit higher because our total dynamic height is of course lower than 35 feet, but this is a realistic number then. Now, with this information, we can calculate the hydraulic energy that we need as we calculated the pumping head was 15 meters and the maximum volume of 10.5 cubicles per day, then we need 0.43 kilowatt hours per day. Now, please remember that we said earlier that we need more electrical energy to compensate for pump losses, typically between 30 and 60%, as said before, and in our example it's 35, so we need 1.2 kilowatt hour electrical energy need per hour. Then what we do is we take the tool and we look in Paracao Benin the minimum peak sun hours, and during the month of August it's about 5.3 hours sun per day. So with these figures we need 1.2 kilowatt hours a day, and with some calculation a minimum PV array that we need is 400 watt peak, and in the example we decided to connect 2 solar panels of 300 watt peak, so we had 600 watt peak altogether. So here is the pump controller that we used in the Benin example. It is a MPPT controller with DC to DC converter. Remember that the MPPT controller is a very efficient controller where it gives you the optimal input while the conditions of course vary with the solar, if clouds float by and so on, and MPPT controller is efficient with that. It supports variable speed according to the PV input current. It contains a float level switch which can be on and off, a dry run protection, low voltage and reverse polarity protection, and you can set the rounds per minute in case of battery mode. And the controller works at 48 DC, input voltage max 105 volts, and input current max 17 amp. And of course the voltage is important, dependent on how many solar panels you put in series. You have to make sure that the peak voltage can never be larger in this setup than 105 volts. And if the setup is such that there is a danger for that, then instead of putting the panels in series, you can put them in parallel. So we're going to look at the PV model that we used in this example. It was a module with 72 cells, and we have here the specification of the cells. By the way, this is usually put on a sticker on the rear of each panel, so for the most panels you can look that up very easily. If we look at the maximum voltage, one module will do at the highest 44 volts. So that means if we put two in series, we have maximum 88 volts. And remember that we could maximum have a voltage of 103 volts, so that's okay. But you see, if we would have 3 of these panels in series, we would exceed the controller input voltage. And if we look at the current, one module could max deliver 8.4 amps. So that will be okay. If we put 2 in parallel, we would have 16.8 amps, also still within the specs of the controller that we just saw. And we see if we put 3 in parallel, we will exceed the maximum current input for the controller. So here you see the system as we proposed that for Benin. We had 2 PV modules in series, total 600 watt peak. We have the MPPT controller that we presented, and we had a positive displacement pump. So after this example, we're going to do an exercise together. First thing we consider is how to read a pump performance chart. We show you here the charts of 2 different pumps, where you see the daily amount of cubical meter next to the head, and you see there are quite 2 different curves for each pump, a different curve. Okay, assume 200 watt peak solar power, 10 meters head, and pumping during 5 hours per day. Look up the flow rates per day for each pump. Which pump delivers more water? Which pump is more efficient? So, I leave it to you to calculate that, and we will review the answers later. So then we have another example that I want you to look into offline. At the farm at Mangororo, Tanzania, a diesel pump delivers water for maize irrigation with a daily demand of 22,000 litres. The water is pumped for a depth of 65 meters into a storage tank of 10 meters high. If one would apply a solar pumper system, how many solar panels would be required if we take into consideration that each solar panel has 300 watt peak? So the questions are, define the solar production in Morogoro with the PVGIS tool in kilowatts per day for a 300 watt peak solar panel, and calculate the required number of solar panels. You can see the basics chapter 5.2 and this presentation. Try to check the calculation with the design pump sizing tool and exploring the tool. We will not review that in this presentation. Okay, time for a summary. As we said, water pumping is in most cases cost effective, typically 40% cheaper compared to diesel and wind power pumps. The capex is higher, but operating costs are much lower, and at this moment we're looking at a payback time of less than 4 years. Important to realize that providing systems are operating daily, for instance for drinking water. We have advised to use online tools for system sizing, and there are also portable solar pumps which can help small farm holders. I also advise you to look into these information sources that are available on the net. Thanks for listening, and hope I've been able to make things clear to you. Thanks for watching.